Okay, we're going to get started on filling out the other column of the test, the other column of this graphic organizer, which is significance tests, right? So the two different types of tests that we run: confidence intervals, where we're estimating a proportion or a mean, and significance tests, right, where we have hypotheses. All right, so we have the same 4 parts: state, plan, do, and conclude. They just include different things with significance tests. So here, instead of stating the parameter we want to estimate, we're going to state our hypotheses. And we have 2 hypotheses, right? We have the null and the alternative. So you're going to state what they are, and you're going to state them using the parameter that you use for the test. For proportions, your parameter is p. For means, your parameter is mu. Right? So an example of H null could be that P is equal to 0.5, and your alternative example could be that P is not equal to 0.5. And that would be a 2-sided test, right? Because it could be not equal to 0.5, it could be below 0.5, or it could be above 0.5. So that would be 2-sided. An example of a 1-sided alternative would just be P is less than 0.5. All right. So once you've stated your null hypothesis and your alternative hypothesis, you need to define the parameter in context. So what I want you to do here is basically say where P is the true population proportion of people who have dogs, right? Use what they give you in the problem to define the parameter. Then you're going to state your significance level. Remember, that's your alpha level. They'll tell you the alpha level in the problem. If they don't tell you, you can assume an alpha level of 0.05. All right. Plan. You're going to name the test again. It's pretty similar to these names over here. It would be a 1 sample blank test for blank. And again, it would be a z-test for proportions, and it would be a t-test for means. So the only difference here is instead of saying interval, we're saying test. So 1 sample z-test for proportions, or a 1 sample t-test for means. All right, our conditions that we're checking, we're just going to write same as confidence interval. I'll review it really quick just so we can make sure that we understand. You've got 3 conditions, right? Your random condition. The problem needs to state that a simple random sample has been taken, and that's so that we can generalize to a population. The 10% condition, our sample needs to be less than 10% of the entire population we're taking the sample from, right? Because if we're sampling without replacement, which most samples do in the real world, then we can't assume independence. And if we can't assume independence, then we can't use these formulas. So this is sort of our exception, saying if our population or our sample is less than 10%, then it really doesn't matter because it's essentially independent, right? Our third condition is normality, so that we can assume a normal distribution and use those the table A and table B. So with proportions, it's the large counts condition. Your successes and your failures have to be greater than or equal to 10, right? So your sample size times your p hat, and your sample size times your 1 minus p hat. Now, if we're in the world of means, then if your population is approximately normal, you can assume the sample is normal. So you could just state population is approximately normal. But they would have to tell you in the problem that the population that your sample is coming from is approximately normal. If they don't do that, then we can also assume normality using the central limit theorem, right, CLT. So if our sample size is greater than or equal to 30, CLT applies. All right, so what if they don't say our population is approximately normal and our population is smaller than 30? What do I do then? Well, I can still meet the normality condition if my sample has no strong skew or outliers. And I prove that by doing a little dot plot drawing of my samples. And then from that dot plot, you'd look at the shape and see if it has a strong skew or outliers. If it does have a strong skew or outliers, then you're done. You can't do the significance test. All right, the do part. Calculate the p-value. Remember, the p-value is what we're going to use to compare to the alpha level to make a conclusion, right? So we use the basic overall z formula, right? Z is equal to value minus mean over standard deviation. Value minus mean over standard deviation. Here we've changed it to statistic minus parameter, so sample minus population over the standard deviation of the statistic. All right, formula. I'm going to pause and write it out as neatly as I can, and I'm going to write out the formula for proportions and the formula for means, and then we'll go over it. All right, I did a lot of work in 1 second. All right, so here are our two formulas, right? Here is our Z formula for proportions and our T formula for means. All right, so our Z for proportions. Statistic minus parameter over standard deviation of statistic. So p hat minus p all over, and remember p hat comes from your sample. Where does p come from? It comes from your null hypothesis. So your sample minus your null, all divided by the square root of p times 1 minus p over n. Remember, we're using p here because we're assuming the null is true. So whatever you use for p, you're also plugging in down here. So p times 1 minus p all over n, which is the sample size, and this square root goes over everything. And that is how you get your z-score for the p-value. For means, you're getting a t-score. So your t-score would be your x bar, which comes from the sample, right? Your sample mean, minus mu, which is coming from your null hypothesis, right? It's what the null hypothesis says the mean is, the population mean, all over s of x, or the standard deviation of x, divided by the square root of n. And remember, n is our sample size. And these two formulas in the denominator come from Miss Keen's graphic organizer, the one that she went over in the previous video, right? They're the standard deviation formulas for sampling distributions, if you're wondering where those are coming from. All right, I always recommend drawing a picture so you know if your alternative hypothesis is one-sided or two-sided, because that's how you'll need to know when you're finding the p-value. So I've got 3 different scenarios here. The first one is one-sided to the left, right? So if your alternative hypothesis said anything about p being less than the null, then or at most this would be your picture. This is also one-sided, but this is to the right. So your alternative hypothesis might be that p is greater than the null, right? Or at least this. And then here's our two-sided hypothesis, right? Which was my example up here. P does not equal 0.5. It could be lower than 0.5, or it could be higher than 0.5. It just doesn't equal 0.5. So here's the one-sided, and two-sided. All right, when you get your p-value, you're going to go back to your your z-score. You're going to go back to your table A, and you're going to hang on. Okay, so you've used this formula to get a z-score for your proportions, right? So say, for instance, your z-score is one-sided to the left, and it's negative 1.52. You're going to go to negative 1.5, and you're going to go over to 0.02 right here, and this would be your p-value, 0.0643. All right, so that's the easiest scenario. That's the one-sided to the left. You just take the number straight from the table, depending on what your z-score is. All right, now what about a one-sided to the right? All right, let's say my one-sided z-score to the right was 2.43. So I got a z-score of 2.43. So 2.43 would be right here. Yep. 2.43 is 0.9925. Well, looking at this picture up here, 0.9925 is everything to the left of the z-score, right? In our picture, we shaded to the right because of what the problem said. So for this scenario, you're going to have to do 1 minus the probability from the table A. 1 minus that probability, or 0.99 whatever I got. What did I get? 0.9925. 1 minus 0.9925 would be my my p-value there. And that's because we shaded to the right, not the left. All right, our two-sided. So let's say that we got our z-score of negative, remember, this would be a negative z-score and this would be a positive z-score. How do we know? This right here is to the left of the mean, so the z-score would have to be negative because it's below the mean. This is positive, meaning that it would be above the mean, right? So you'd have two potential z-scores. Say your z-score is negative. Go back to the chart, pull that negative z-score, figure out what the probability is, and multiply it by 2. Multiply that probability by 2 because you have two sides. Now, if your z-score is positive, you have an extra step. You're going to go to that positive part of the z-score table, find your probability, and you're going to do 1 minus the probability. That's step number 1. Step number 2 would be taking that number, step 1, and you're going to multiply it by 2. So your step 1 number times 2. And that's because it's two-sided, right? So we do 1 minus the number in the table because we found the z-score shaded to the right. So it's just like this scenario right here, but we need to multiply it by 2 because I have a two-tailed alternative hypothesis, right? So you've got 4 different scenarios. One is a one-tail shaded to the left. Just take the number from the table. The second scenario is one tail shaded to the right. You're going to do 1 minus the number you find in the table. Alright, or you've got a two-tail. If your z-score is negative, just take the number from the table and multiply it by 2. If your z-score is positive, you want to subtract the number you find by from 1 and then multiply that number by 2. I know that's a lot, but hopefully that helped. Alright, for the conclude part, is the p-value larger or smaller than the significance level? Well, we just calculated the p-value here, right? So we look back up here, and our significance level, if it doesn't tell us, is 0.05. If your p-value is less than the alpha level, you're going to reject the null. If your p-value is greater than the alpha level, you're going to fail to reject. Fail to reject the null. Alright, so small p-value means that we have evidence for the alternative. A larger p-value means we do not have convincing evidence, right? So smaller p-value, we reject the null. A larger p-value, we fail to reject the null. I'm going to go ahead and write out sentence stem, and I just now realized I didn't go over how to calculate the t-value, so I'm going to grab my calculator and we'll go through that as well. Okay, so I went ahead and wrote down the sentence stem of interpretation, and it's got, it looks ridiculous and large because I wrote both options, so you'll need to know what to choose based on your p-value, right? So interpret results. Because the p-value of, let's just say 0.02, because the p-value of 0.02 is smaller than the significance level of 0.05, we reject the null hypothesis. We have convincing evidence that the true proportion or mean is greater or less than or different than the null. Alright, so let's break that down. We are rejecting because the p-value is smaller, right? If the p-value was larger than the significance level, we would fail to reject. Since we are rejecting, we would have convincing evidence that the true proportion or mean is different than the null hypothesis, right? So I put all of these words first because they go together. Smaller, rejecting, and have. The other words go together. Larger, fail to reject, and don't have. Alright, so you would use these circled words together and these underlined words together, all depending on whether or not your p-value is bigger than your alpha level.